Hello everyone, welcome to my new video. So today I am going to solve the question paper of Iiser Pune MSc entrance test. Okay, so the first question is that it is the part of the subjective question paper. Okay, let T from Rn to Rn be a linear transformation and show that T is nilpotent if and only if the matrix corresponding to T with respect to some basis is strictly upper triangular. With respect to some basis. Okay, so the solution. So if with respect to some basis the matrix T, say with respect to this basis, is strictly upper triangular, then it must be something like that. Or something, any entries are there, right? This is some n by n matrix. Now clearly eigenvalues of upper triangular matrix are diagonal entries. Now here all the diagonal entries are 0. This implies all the eigenvalues are 0. This implies the characteristic polynomial is lambda power n equals to 0. Okay, and then it will imply t power n is 0. Hence, t is nilpotent. Now come to the converse part, which is the most interesting. Given that T is nilpotent, that means T power k equals to 0 for some k. Clearly, determinant of T power k is 0. That will imply determinant of T is 0. It will imply there exists some V1 belongs to Rn such that T V1 equal to 0. That means there exists some non-zero vector, obviously non-zero vector of Rn, which is inside the null space, right? Since T is nilpotent. Now claim is that there exists V2 doesn't belong to span of V1 such that TV2 belongs to span of V1. This is a claim. If not, then for all x doesn't belongs to span of V1, Tx doesn't belong to span of V1. That means for all Tx doesn't belong to span of V1, T square x doesn't belong to span of V1. I can just replace x by Tx, and in this way I can replace x by T power k minus 1x. Then it gives that T power kx doesn't belong to span of V1. But T power kx is 0 because T is nilpotent and T power k is identically 0. That means t power kx is 0. But it says that 0 doesn't belong to span of V1, which is a contradiction because span of V1 is a subspace. So 0 is always there, right? Hence this is the contradiction. That means this claim is true. So that means you can always find a V2 which is not in span of V1 such that T of V2 belongs to span of V1. Okay? That means V1, V2, this set is linearly independent as V2 is not inside the span of V1 and T of V2 belongs to span of V1. Now you can do an induction. So you can show inductively that in this way, next step will be choose V3 doesn't belong to span of V1, V2 such that T of V3 is in span of V1, V2. Okay, and so on. So finally you will get that finally in nth stage you get a basis such that T of Vi belongs to span of V1 to Vi minus 1. Now if you write matrix representation of T with respect to this basis B, what will you get? How to write that? So T of V1 is 0, T of V2 say C2 dot V2, C2 dot V1 because T of V2 is inside span of V1. Okay. This is C12. T of V3 is C13 V1 plus C23 V2 and so on. Okay, and so on. P of Vn equal to C1n V1 C2n V2 and so on. C1n minus 1 Vn minus 1. If you write down the matrix representation, what will you get? You will get 0 C12 C13 C23 C14 C24 C34 and so on. C1n C2n C1n minus 1 with diagonal entries 0 and lower diagonal entries also 0. That means strictly upper triangular. This is the nice one. Okay, go to the next one. Let P be a prime number. Suppose that order of each element of a finite group G is a power of P. Then show that G is a P group. If G is not a P group, there exists a prime Q not equals to P such that Q divides order of G. Now by Cauchy's theorem, there exists an element of order Q is inside G. This will imply, this will contradict our given condition, because our given condition says that order of each element of a finite group G is the power of P. But here we find an element by existence, by Cauchy's theorem, such that that element has order Q, which is not equal to P. So Q is not a prime power. Where Q is not a prime power. Q is not P power K for any K. Right? So hence G has to be P group. G is a P group. Okay. The third one is that R be a commutative ring with 1 for any A, and depending on A there exists a natural number n such that A power n is equal to A, so that every prime ideal is maximal. Let I be a prime ideal, then R mod I is an integral domain. Choose alien. So if I can show that R mod I is a field, then we are done. Let x plus I be an element. And x plus I power n equal to x power n plus I, which is equal to x plus I. So if I write x plus I as y, which is an element, then y power n equal to y, which implies y into y power n minus 1 is 0. Now x plus I be an element of R mod I, and R mod I is an integral domain. So in an integral domain, product of two elements is 0, imply either one is 0, right? That means it will imply that y is 0 or y power n minus 1 is 1. So it will imply y is unit. Every non-zero element of R mod I is an unit. So it will imply R mod I is a field. This will imply I is maximal ideal. Okay. Now the problem number 4, which says that it has two parts. So we define a notation f prime x dot y, the directional derivative at x in direction of y. Okay, this is just a notation. Then the part A says that there is a scalar field f such that this quantity greater than 0, this quantity is greater than 0 for a fixed vector x and for all non-zero vector y, and second part is there is no scalar field f such that this quantity is greater than 0 for a fixed vector y and every vector x. Okay. So the solution, so f is a scalar field. That means f, say from Rn to R, be a differentiable map. What is gradient of f? Del f del x1 del f del xn, right? So this quantity, that means directional derivative at x in direction of y is same as y, means I equal to 1 to n yi times del f del xi. Now come to the question. There is a scalar field f such that del f del x f such that this quantity greater than 0 for a fixed vector x and for all non-zero vector y. Okay. So without loss of generality, I can assume that del f at x is non-zero, because if del f at x is 0, that means, sorry, if gradient of f at x is 0 vector, that means if this quantity is always 0, which is not possible. So without loss of generality, I can assume that gradient of f at x is non-zero. That means there exists some I such that del f del xi is non-zero, because this vector at x is non-zero. That means there is some quantity del f del xi which is non-zero at point x, right? So without loss of generality, I can assume that del f del x1 is non-zero. Without loss of generality, assume del f del x1 x is non-zero. Now choose a vector y equal to 1 0 0 0 0 this. If del f del xi is non-zero, then you will choose that vector which has that ith component is 1, other component is 0. Basically the basis vector, ith basis vector, okay, of Rm. Then what will you have? For this particular y, we have del f del x1, right? And for this y, if I take y to be minus 1 0 0 0, we have minus del f del xi. Now since del f del x1 at x is non-zero, both of these cannot be greater than 0 together, right? Hence there doesn't exist any scalar field f. Okay. And for the second part, you can also do something like that, that there is no scalar field f such that for a fixed vector y and every vector x. So you can take say the projection map xn to be say x1, okay. That means for every vector x, gradient of f is basically 1 0 0 0 this, okay. And for every vector x, the gradient is 1 0 0 this. And if you choose a fixed vector y, say if you choose y to be something with first component is positive, anything like take 1 1 1 1 this thing, then this is always 1, which is greater than 0 for every x. So you can construct such a scalar field. But the important part is that you have to understand that how it looks like. Okay, so if you can think in this way, then it will be easy for you to understand. Okay. Now the question number 5 is a very simple, easiest question, that f from R to R is a differential map such that f0 equal to 0 and f of 1 equal to 2. So by mean value theorem, there exists C belongs to 0, 1 such that f prime C equal to f of 1 minus f of 0 by 1 minus 0, which is 2 minus 0 by 1, which is 2. And there exists some t belongs to 1, 2 such that f d such that f prime d is f of 2 minus f of 1 by 2 minus 1. F of 2 is 1, f of 1 is 2. Means it is minus 1. Now we know Darboux theorem. It's a very important theorem, right? For derivative. The derivative map always satisfies the IBP. Right? That means there exists some x, or there is some t belongs to C comma d such that f prime d is 0. Because f dash d is minus 1 and f dash c is 2. That means there is some t such that f prime d is 0. And this is the last one, question number 6. Integral 1 to infinity cos t by t dt is convergent but not absolutely convergent. To show that convergent, you can just integrate it. Let's see what we will have. We'll get right. Now observe that sin t by t squared dt is less equal to less equal to 1, right? And this will imply that integral value 1 to infinity cos t by t dt is convergent. This integral is convergent because this quantity is finite, this quantity is also finite, so it is convergent. But it is not absolutely convergent, which is the most important part. But this is not absolutely convergent. That means this integral doesn't exist. This integral doesn't exist. How can I show that? So fix k greater than 0 be a natural number. So there is no point of writing greater than 0. I mentioned already natural number. Okay, a be a natural number. Let integral 1 to 2k pi cos t of t dt is equal to 1 to 2 pi mod of cos t by t dt plus 2 pi to 2k pi cos t by t dt. Now this quantity can be written as summation I equal to 1 to k minus 1 integral 2i pi 2i plus 1 pi cos t by t dt. So now take this part, first part. So cos t by t is continuous on 1 to 2 pi. That means it has a maximum value. So that means mod cos t by t is equal to m on integral 1 to 2 pi. So then I can say that integral 1 to 2 pi cos t by t less dt, this is less equal to 2m pi, which is some finite quantity. Okay? It's less equal to 2m pi. So this part is fine. But what about this part? This part is most important. So we have this part I equal to 1 to k minus 1 2i pi 2i plus 1 pi mod cos t by t dt. Okay. Okay. Now observe t belongs to 2i pi comma 2i plus 1 pi. That will imply 1 by t less equal to 1 by 2i pi, not less equal to, and indicated equal to equal to 1 by 2i plus 1 pi. That means this integral value is greater equal to summation I equal to 1 to k minus 1 2i pi 1 by 2i plus 1 pi integral 2i pi to 2i plus 1 pi mod of cos t dt. Now what is this value? See, if you draw the picture of mod cos t, you will see that, say, this is 0, this is 2 pi, means mod cos t, right? So it is, say, pi by 2, something like that, right? If I am not wrong, this is the picture. This is the graph of mod cos t. So if you integrate it on 0 to 2 pi, which is same as 2 pi to 4 pi, which is same as 4 pi to 6 pi, we will get 4. That means this integral value is greater equal to summation 4 times I equal to 1 to 2 1 to k minus 1 1 by 2 times I plus 1 pi. Okay. So that means clearly 1 to 2k pi cos t dt is greater equal to 4 times summation I equal to 1 to k minus 1 1 by 2i plus 1 pi. Now this term is divergent. That means as k tends to infinity, we will get 1 to infinity cos t by t dt is divergent as this series. So k tends to infinity, this series means this series becomes summation I equal to 1 to infinity 1 by 2 of I plus 1 pi. It's a divergent. That means this one is divergent. Okay. And this term doesn't contribute. This is just a factor of just a constant term. I mean, you can just take it as bounded by some finite value. So this doesn't contribute. So this is dominated by this term. So I mean, this integral value is greater or equal to this term. So that, and this series is divergent. Hence this integral is divergent. So that means it is convergent, but not absolutely convergent. Okay. So that's all 6 problems of the subjective paper of Iiser Pune MSc Entrance Test. If you have any doubt, just comment below.